Welcome everyone to the last PYSQT seminar of this year. In this occasion, we are having an invited speaker, which is Tony Acín. Tony is a research professor at ICFO, the Institute of Photonic Science in Castelldefels. And just to give a brief introduction to who's Antonio, Antonio got his degree in physics in the University of Barcelona and a degree of telecommunication engineering in the University Polytechnic University of Catalonia. He did a PhD in theoretical physics from the University of Barcelona, and afterwards a postdoc in Geneva. Since 2003, he's in ICFO, leading the group in quantum information theory. Now we can, Antonio, when you want, the stage is yours.
Okay, thank you very much for the introduction. I now see some people that I know here, like Alex Polfas. I'm not sure if the talk is going to be of his interest because, I'm going to give a rather introductory talk. So it could be that I believe that this is addressed mostly to PhD students. So this is a talk that I gave already in several conferences, but maybe for some of you, the first time you see this talk. So I hope you will find it interesting. Okay, for those who have seen some of my talks, maybe it will be redundant, so feel free to leave if this is the case. So yes, I will start by sharing my screen and the slides. I guess it's not easy to, I always like talks in which people interrupt the speaker. I'm not sure if this is going to be possible.
We leave you the choice as you prefer.
Well, for me, it's fine. Yeah, no, I'm not sure if... Can you see my slides?
Yeah, we can see them.
Okay, very good. Well, if you want to interrupt me, I think this is better. If online sometimes it's not easy, I think it's better because if you have a question, some other people looking at the talk may have the same question. So I think it's good if we.
It's great. It's up to you. It's up to you. If you want so, then everyone in the audience is.
Yeah, feel free to do it. I don't think we are so many, so we can do it. Okay, let me just do something before I start. Something, but no. Well, okay, it doesn't matter. Okay, let's start. Yeah, so well, thanks for the invitation. It's always nice to talk to young people. So the purpose of my talk is to tell you about what is called here the device independent scenario, which is something which my group and other groups in Europe and in the world have been working on in the last year. So it's one of our main themes. So I thought it was a good opportunity to introduce this scenario in general terms to this audience. Yes. Okay. So I will start very basic. So what is quantum information science? It's basically the field in which you want to study what happens when you make the transition for information devices. So physicists already made the transition in the past by this is why they invented quantum theory, right? So they wanted to describe what happens to nature when you go from our world to the world of atoms and photons and electrons, and they had to invent a new set of rules, and this is quantum physics. Quantum mechanics. And now the same transition, we are implementing the same transition for information devices. And we see that since the physical laws governing the devices are different, we can do with these devices, we can do different protocols, and we can find different applications for information processing with these devices. Okay, so what we can do with quantum devices is not the same as we can do with classical devices. I guess you are familiar with this message. And what we now know is that you can have more powerful computers and you can have a new form of secure cryptography using quantum effects. Okay, and whenever I give the sort of general audience talk, I like to spend some time here in this because I think it's one of the main messages in quantum information science, which is that physics matters. Okay, so if you had asked me, well, as it was mentioned during the introduction, I'm a telecommunication engineer and a physicist. I never had any course on information theory while studying physics. And this was because before quantum information, although information is a key concept in physics, we always understood that information has nothing to do with physics. Okay, so the works by Shannon, I never saw any work by Shannon on coding theorem or on channel capacities when studying physics. And perhaps one of the merits of information theory is that we always thought that it is independent from physics, but actually this is not the case. It's right the opposite. Okay, so physics matters, and what you can do with information depends a lot on the physical properties of the devices you use for information encoding. Okay, so this is a change of paradigm. And then, okay, we know that quantum information technologies have evolved. So now we have quantum information science, but we also have technologies based on quantum information. And you can even buy some of these technologies. So you can go to some companies and they can give you a device where they tell you this is a quantum computer. You can also buy a device where they tell you that this implements a quantum cryptography protocol. You can also buy a device in which the company tells you you have a device that generates randomness according to quantum physics. And but perhaps it's less commercial at the moment, but we also have in many labs, we have systems in which scientists try to design a setup to simulate another quantum system of physical interest. We have quantum simulators. Okay, so we have all this plethora of applications, sometimes at the commercial level. And okay, what you can see here is that you are given these applications, no? But then a very natural question is one of about, okay, how do I know that these devices work as expected? Because the problem we have is that the way we reason at our scale is using classical information, and usually we test the devices we buy with classical information devices like your laptop or your computer or even your information, and we deal with classical information. So we want to understand if these devices, either those that are given by providers or those that you prepare in the lab or an experimentalist prepares in the lab, so if you are a theorist, we want to understand if they achieve what they are expected to achieve. Okay, so then you want to know whether this is a quantum computer, this is a quantum cryptographically secure, this is random, quantum random, or whether this properly simulates a quantum system. Okay, and this is a relevant question. I think it's a fascinating scientific question because somehow it's challenging because, I don't know, for instance, if you have a many-body quantum system, we know that a perfect reconstruction of the many-body state is simply impossible. So you have to deal with your poor and limited classical information devices, and you have to deal with these complex quantum devices, and you want to certify that they're correct functioning, or you want to understand their properties. It's also a relevant question, not only scientifically, but also technologically, because you will buy these devices from providers, and you want to make sure that they work as expected, because you are going to pay a lot of money for these devices. Okay, so this is also another possible motivation for you to consider the problem of quantum certification. And of course, another motivation is like, eventually, when we have these devices, we will also need to design standards, okay? Because you want to, again, certify the devices work as expected. And then you have to really understand what makes these devices special when compared to other computers that do not use quantum properties, or to other cryptographically or random devices that do not use quantum properties. And okay, many of you, possibly you have seen this joke because I use it a lot, because I find it really, it makes the point of my talk. Okay, so this is like, this is one of the possible applications of my previous slide. So there is you are a client, you go to a provider and you want to buy a quantum random number generator. And let's assume that this is the quantum random number generator. And of course you will wonder whether this is random. And then the provider, okay, here the provider the provider is classical, and he says that you can never be sure around randomness, which is true in the classical world. But what we want to see is that you can be certain about randomness in the quantum world, which is, it seems like a paradoxical statement, but you will see that it's not, okay? And again, what happens here is that you, as a client or as a scientist, you have access to a quantum system, and the way you want to extract conclusions about this system is from the statistics it produces, because if you buy a quantum random number generator from a provider, the provider will give you a box. And then you will ask the provider, okay, is this a proper quantum random number generator? And in principle, the provider will tell you, yes, okay? And you want to and you are never going to open the device, and because you don't know about what's inside the device, and sometimes you cannot even open it, and you're never going to see if the mechanisms producing randomness, okay, what is inside the device is really of a quantum origin, okay? And even if it was, okay, what it was supposed to be, it could be that the mechanism is not working properly, and then even if you thought that the randomness had a quantum origin, you don't have it. Okay, just wait a second because I have to take some water. Just a second. Okay, good. Sorry for the interruption. So as you will see during my talk, one wants to certify the presence of quantum randomness, or more in general, we want to certify quantum devices from the outputs they produce. Okay, in this case, the 99999. So this is the main purpose of this quantum certification problem. And now I'm going to focus on a possible quantum information application, one of the main quantum information applications, which is quantum key distribution. Okay, so this is the process in which two honest parties, Alice and Bob, run a quantum protocol to distribute a secret key in a secure way. You don't need to, I guess many of you know about BBT4 because I guess any PhD student in quantum, for sure in quantum information theory, but even on experimental aspects of quantum information processing, knows about standard quantum key distribution protocols like BBT4. So what is important here is that the security of the protocol is based on the fact that Alice, Bob, but also the honest users, but also the enemy, the eavesdropper, Eve, they are using devices that are governed by the laws of quantum physics. So using this assumption, you can prove the security of the protocol. So the protocol is based on physical security, on the validity of quantum physics. So you make an assumption, which is that quantum theory offers a correct physical description of your devices. And then you don't have to make any assumption on the computational power of the eavesdropper. She can do whatever she wants, of course, without violating quantum physics. Okay, and then using this, you can prove the security of quantum key distribution protocols, which is something very nice. And then, okay, this was one of the main merits of quantum key distribution from a theoretical perspective. Implementations came. It's a technology that is more mature than others because it's simpler to realize. And there are even companies selling you quantum cryptography based on quantum key distribution. Very nice. So we have a security proof. What happened already almost 15 years ago, 13 years ago, is that there were several teams of researchers who went to these companies selling quantum cryptography, and they bought these devices, and then they showed that they could hack them. Okay, so I think the main person in these hacking attacks was Vadim Makarov and co-workers, but there were several teams doing this, reporting these hacking attacks, and they made nice publications, and of course people highlighted these results because they were very relevant. Okay, if you think about it, a cryptographic solution is not mature until it does not face hacking attacks. Okay, but what I was telling you before is that for quantum cryptography, there is a security proof, which is based on the validity of quantum physics. Okay, so here we have to understand that something, I mean, I'm lying to you, or there was something we didn't properly understand. Okay, and there are several possibilities. So you may think that what the hackers did was to prove that quantum physics was wrong, and then they could hack the protocol because this assumption was not correct. But this is not what they did, because I mean, we still use quantum physics, and we still believe that quantum physics is the right theory to describe the physics of the devices you use for quantum cryptography. So security proof is a mathematical proof. So you may think that Makarov found a mistake in the security proof, but he doesn't look like a mathematician. You see, I mean, all these devices he has around, he is an experimentalist. So there was another option, and this is what we understood after his attack, okay? And this is what I'm going to tell you, okay? So what happened is that what the quantum hackers managed to do, they were able to break the implementation, but not the principle of quantum key distribution or of quantum cryptography. So what do I mean by this? So if you look at any quantum cryptography protocol, if you know about BBT4, think about BBT4. In these standard protocols, you have the honest user, say Alice. She prepares states that are in a Hilbert space of a given dimension. So she prepares qubit, Hilbert space dimension 2, and she sends these qubits to Bob, and Bob makes measurements on these qubits, and these measurements are described by standard spin 1/2 measurements that is by a basis on this Hilbert space of dimension 2. Okay, and this is, you simply state the protocol using these ingredients. Alice has to prepare some given states, Bob has to make some given measurements, and then they have to follow some steps, and their security proof tells you that the protocol is secure. Now, what happens in reality when what does the provider do when preparing the devices to implement a protocol like BBT4 protocol? Well, I mean, in principle, the provider has to prepare devices that prepare states in a Hilbert space of dimension 2, okay? Well, I think this is simply impossible, okay? You can never be sure that something lives in a Hilbert space of dimension 2 because any system has infinite degrees of freedom. Of course, when you prepare a qubit, you make sure that most of the relevant information is, say, on 2 of the possible degrees of freedom, but there are always many more variables in your system. Like if you think about photons, which is usually what Alice and Bob use to encode information, photons have polarization, say a degree of freedom of dimension 2, but it also has frequency, it has also orbital angular momentum, but it has many degrees of freedom, okay? And it's not true that you are preparing states in a Hilbert space of dimension 2. It's a very good approximation, but it's not true. And actually what the provider does is usually they use states that are produced by an attenuated laser source. And of course, a laser source is not an object living in a Hilbert space of dimension 2. And then the measurements you implement are you use, say, single photon detectors. And for sure, single photon detectors is a complex object that does not live in a Hilbert space of dimension 2 either. Okay, so what happened here is that you have a theory and that a theoretical description of your protocol in which you prove security that is here, but you see the implementation does not perfectly meet the requirements you need in the theoretical security proof. So somehow for the hacker who is interested in hacking the implementation, the security proof is, well, you could even say irrelevant. I mean, maybe irrelevant is a too strong word, but what I'm saying is that the theoretical proof applies to the theoretical implementation, but to the theoretical description, but it does not apply to the implementation because the conditions under which the theoretical security proof has been established are no longer true in the implementation. Okay, so the theoretical security proof does not apply to the implementation. Hence, hacking attacks might become possible, and indeed, the hackers prove that they are possible because of this gap. Okay, so what we learned from these hacking attacks is that the mismatch between a theoretical description and implementation might be a weakness, especially if you are dealing with protocols in which you are fighting against an enemy, as is usually the case for cryptography application. Okay, this is maybe for computation may not be such a relevant issue, although some of the things I'm going to say also can be used for the certification of computers and simulators. But it's for sure a very important issue when you are dealing against an enemy. And somehow what we learned in this process is that, of course, it's very nice that it was very nice to understand that physics matters for information processing. But if your application relies a lot on all the physical details of your physical implementation, then this might be a problem, especially if you're fighting against a witness. Okay, so the physical details, the physical modeling of your devices, the fact that you need a very careful modeling of your devices for a protocol to be successful might be a weakness in your protocol performance. Okay, because if you don't manage to make every single detail of the implementation to match the details of your physical description, then this may open loopholes, and these loopholes may be exploited by your enemy. Okay, so what's the solution for that? Well, I mean, what we have to do, we have to minimize this gap. Okay, so we have to make a description of protocol in which we don't make any assumption on the devices. Okay, so our modeling of the devices is the minimal possible. So we don't want to say that the device lives in a Hilbert space dimension 2, 3, 4. We will work with no dimension, and we won't specify the measurements that the parties implement. We won't specify the measurements of the states of the parties prepare. So we just want to model devices in a very minimalistic description. And this is what we proposed already some years ago in 2007, which was the solution to the hacking problems as I've just described, okay? And this is the idea of device-independent quantum key distribution. So you will describe your devices as simple black boxes, and these black boxes, you won't say anything about these black boxes. They are quantum black boxes, okay? But they cannot contradict the laws of quantum physics, but you don't know what's going on in these black boxes. And of course, okay, then you will have your honest users, and they will have devices. They want to implement a quantum key distribution protocol with these devices, okay? And of course, these users, they have to be given the possibility of interacting with these devices, and they will do it in the way we users interact with devices, which is through classical information, okay? So the users will be given the possibility of sending classical information to the device will do some processing, quantum processing of this classical information, and will produce an output. Okay, so here there is some quantum process. I don't know what's going on in my device, and I don't want to know, and I don't want my protocol to depend on what's going on here. This is why we call it device independent. And at the end of this process, I read the result, and we read classical information. So this is what I get here. Okay, so, and this is what Alice does and what Bob does with the devices. Okay, they choose some classical information, they feed the devices with classical information, and they get some classical information out after the devices interact with the input, okay? So we have an input-output process, and the way we describe this input-output process is with just probabilities, okay? So we have probability of observing a given result on Alice's side and another given result on Bob's side, depending on the action that Alice chose for her device and Bob chose for his device, okay? This is probability of result AB given XY. Now, if you have a protocol, a quantum information protocol, that achieves a given goal only from the statistics you see, only from the probabilities of having outputs given the inputs, and without making any assumption about how this output is produced given the input, then you are insensitive to the hacking attacks by Makarov, okay? Because there is no mismatch between your theoretical description and your implementation, because if your implementation gives the statistics you need for the theoretical protocol, and this is all what you need for the theoretical protocol, then there is no mismatch between theory and implementation, and the hacking attacks exploiting this mismatch are no longer possible. So I hope this is more or less clear. Maybe it's a good point for you to pose questions if you have any. Otherwise, I will proceed. Good. I proceed. And more in general, I was presenting this from a quantum cryptography perspective, but we elaborate on this formalism, and we now have a more general scenario in which that is the scenario of device-independent quantum information processing. Okay, so it's just a new type of quantum information theory in which you model the devices by the different users. So these are just black boxes that process a classical input to produce a classical output, again, because we reason with classical information. Of course, behind the scenes, there might be quantum processing, but we feed devices with classical information and we get classical information. And these devices will produce a given statistics, and we want to, only from the statistics, we want to run a quantum information protocol, okay? And this is nice also because these protocols are self-certified, okay? You don't need to put any trust on the provider. If the protocols produce the statistics you want, which you can certify with your limited classical information capabilities, then you know that these devices work as expected, and that you can use them for the protocol you had in mind. Okay, so sometimes I also call this is a sort of quantum information theory with black boxes, okay? Because you see here, I'm not also quantum information theory with no Hilbert spaces, okay? Because I'm never going to specify the details of the Hilbert space, states, and measurements that are taking place in these devices. Okay, how come we can do things in this formalism? Well, this is because in quantum physics, we have something called Bell theorem, okay? And this is also I mean, this device-independent quantum information processing, you can understand it as a Bell-based quantum information theory. Okay, so in the scheme, my narrative before, I was telling you that you are, or Alice and Bob are the users, and they go to the provider and they get some devices. Okay, so the provider prepare the devices, and these devices are given to the users, and the users interact with the devices. They get some statistics, and they hope to prove that this statistic is good for them to run a protocol. Now, what you can do here, you can call now the provider, you can call it a source that prepares two quantum systems, and Alice and Bob generate some statistics from these quantum systems, and this is nothing but a Bell test, okay? So this is something in which you prepare a state of two particles that they will become entangled particles in the quantum case, and you will some measurements and you get some results on these quantum particles. This is a Bell test. So the Bell test is really the language we use, and it's basically, I can talk about certification or about a Bell theorem, and it is the same, okay? So there is no difference between the two scenarios. And one of the main lessons we had from Bell theorem is that the statistics of an experiment, okay, which is, again, of the statistics that the users can see when dealing with black boxes, depend on the physical properties of these measured systems. Okay, and this is because physical principles impose limits on correlations. Just wait a second, because okay, sorry. Okay, so now we have this in mind. So we have all this introduction about certification. I made the connection with Bell theorem. And now I'm going to tell you the language we use in this device-independent quantum information processing, which are these correlations of these statistics that I was telling you about. So we have Alice Bob, or devices. And we have the inputs and outputs. Sorry, I'm interrupted by... And what we have here are the probabilities of the outputs given the inputs. So what is this correlation we have here? Well, you have to think that Alice uses one of the possible inputs, say input 1, and Bob uses input 1, okay? And they see probabilities 1 and 1, with result 1 and 1 with probability the number given here. This is a standard probability, it's a positive number, okay? But sometimes Alice will see result 2 and Bob will see result 1, again, when they both use input 1 and 1, and sometimes they will see result RR with a given probability, okay? All these are just the probability of observing the corresponding outputs given X equal to 1 and Y equal to 1. So these are just simply positive numbers, and they have to sum up to 1. Okay, I'm just telling you what I mean by these statistics of correlations that the parties see, okay? It's just, this is mathematics so far, okay? So you just have positive probabilities, they sum up to 1. Of course, sometimes Alice will use X equal 1 and Bob will use Y equal 2. So we'll have, again, a vector of probabilities for the numbers summing up to 1. And you have all these vector of probabilities for all possible combination of inputs up to X equal M and Y equal M, okay? All of them positive, all of them normalized. This is just mathematics, okay? So I'm going to deal all the time with this vector of probabilities. So again, these are just positive numbers, and all of these numbers that sum up to 1, all these numbers sum up to 1, all these numbers sum up to 1. I will give you an example. So here we have a situation in which Alice will implement two measurements. I will call these two measurements 0 and 1. And Alice and Bob will have two results. I will call the results plus and minus. I could have called them plus 3 and minus 7. This is relevant. This is just labels that we use. Okay. Or I could have called these inputs blue and green. This is just what matters are the probability of seeing this output-input process. Okay. So let's imagine a situation in which they have two measurements of two outputs. And now let's assume that when Alice and Bob use input 0, 0, they get result plus and 1 with probability half. So whenever Alice sees plus 1, Bob has plus 1. This reminds you the process in which you make measurements on a singlet. So whenever Alice sees plus, Bob sees plus, if you measure on the computational basis. Okay, so this is probability half. And I'm going to assume that when Alice sees minus 1, Bob sees minus 1 with probability half. Of course, we also know the values of these probabilities. The probabilities can only be 0 and 0. Okay, so this is a situation in which they both use 0 and 0. you can see this input as a choice of measurement. Okay, they decide to measure on a given basis. Let's assume that the same happens when Alice uses 0 and Bob uses 1. When Alice uses 1 and Bob uses 0. And now I'm going to think that when both use 1, they see only plus minus and minus plus. Okay, I'm just inventing these numbers. Okay, I'm just saying a possible situation in which I describe the statistics produced by the experiment, in which Alice implements 2 measurements of 2 outputs, or she uses an input, a value input, and she gets a 2 value output, and the same for Bob. Okay, do you see anything wrong with this table? Not really. Okay, they are just positive numbers and normalized. Okay, this is mathematics, but now we are physicists, or many of us probably are physicists here. And now I'm going to use physics. Okay, and the nice thing is that you can invent many tables like those ones here. You only have to give positive numbers here that sum up to 1, positive numbers that sum up to 1, positive numbers that sum up to 1, positive numbers that sum up to 1. Now let's use physics. So something that I'm going to do during all my talk, I'm going to assume that what happens in the devices is causally disconnected. So by this, I mean that the input-output process on Alice's side does not depend on what Bob does on the other side. Okay, we may enforce these using space-like considerations, or we may simply assume it. Okay, I'm just saying that the process that takes place on Alice's side is well-defined. It does not depend on what happens on the other side. This is sometimes called the non-signaling condition and give rise to the non-signaling correlation. So these vectors of numbers, or these tables of numbers, have to satisfy some constraints for the physical process on Alice's side to be well-defined. By this, I mean that what Alice sees, the marginal probability, does not depend on what Bob does. Okay, does not depend on Y. So this is saying that, in general, this is the same as demanding that if you sum over the result of a subset of the parties, what the other parties have does not depend on the inputs of the other party. Okay, so you see here I'm summing over the k plus 1 up to n part outputs, and what I see does not depend on the corresponding input. Okay, or what Alice sees does not depend on Bob's input. Okay, this is an easy constraint, linear constraint, but I mean, we give you some non-trivial structure. Okay, so if you look at the table of numbers I invented, if you look at the probability that Alice sees plus 1 when she uses input 0, I can compute this when Bob uses input 0. You see here, I'm just summing over Bob's result when he uses input 0. And if you look at the table, this is the same as the sum of these 2 numbers. So I'm looking at the situation with Alice measures 0, Bob measures 0, and I'm summing over the result of Bob. So this gives me the probability that Alice sees plus when she measures 0. Okay, the sum of these 2 numbers, half. But what I'm demanding is that this number is the same independently of whether Bob measures 0 or 1. Okay, so this is asking that this number has to be the same when Bob measures 1. Okay, so this is the same sum, but I'm changing Bob's input from 0 to 1. And this is the same sum, but now for this row. Okay, you see here the input by Alice is the same. Sorry, yes, I only changed Bob's input and I'm making the same sum over Bob's result. And indeed, this is the case here, okay? And you can see that all these non-signaling conditions are satisfied by this table, okay? So this is an example of non-signaling correlations, but of course, you put random numbers here that are normalized, this condition won't be satisfied, okay? Because equalities are never satisfied by random assignments. So you have to be a bit careful with giving these assignments so that you satisfy all these linear conditions. Good. So these are called the non-signaling correlations. Now, well, let's see what happens before the advent of quantum physics. So before the advent of quantum physics, people thought that these tables that I can invent have to be given by something like classical deterministic processes. Okay, so if what happens in the device does not depend on what the other party does, what happens in the device will depend on the input, the output will depend on the input, and probably something that was inside the device prior to the experiment, okay? And we will call this lambda. So the output is deterministically produced by the input and what is inside the device. And on Bob's side, may depend on his input and possibly something that was written in the device and it was possibly correlated to what Alice has on her device. Okay, but you see, nothing analysis depend on Bob's input, and nothing on Bob's depend on Alice's input. Okay, and while we may think that this varies with time according to a probability distribution. Okay, this is the way I'm presenting you is more perhaps operationally, but this is nothing by the Einstein-Podolsky-Rosen local hidden variable correlations. Okay, and what we know is that this set of correlations have a given mathematical characterization, and what the Bell inequalities are limits that are satisfied by these correlations here, by these statistics here. We are quantum physicists. In the quantum physics, the way we describe a two-part experiment is by saying that Alice implements some measurements, tensor product some other measurements on a state describing the state of the two devices. So I will say that some correlations are quantum whenever I can find a state in a given Hilbert space of two systems. I'm not saying which Hilbert space, but on a given Hilbert space. And I can define measurements for the Hilbert space of one of the devices, tensor product measurements for the second device. And I can combine these objects according to the Born rule, and they give me the statistics I see in the experiment. So then I will say that these statistics, these correlations, have a quantum origin because I can explain them with quantum physics. Okay, again, I'm not specifying that the Hilbert space is of a given dimension. I'm just saying that some correlations are quantum whenever I can find a description in a given Hilbert space. So what do we know about these sets of correlation of statistics? Well, we know that they are convex sets and they are strictly included into each other. Okay, so we know that the set of classical correlations that I'm representing here by this black convex set here is strictly smaller than the set of quantum correlations that I'm representing by this red convex set here, which in turn it is smaller than the set of the signaling correlations. Okay, so if I zoom in, what is happening? This is a set of classical correlations. This is a set of quantum correlations. And this is a set of non-signaling correlations. Okay, all these tables of numbers, here my screen represents the space of table of numbers. And so a table is here whenever it has a classical description. A table is here whenever it has a quantum description. And a table is here whenever it does satisfy the non-signaling constraints. How do we know that this set of quantum correlations is larger than the set of classical correlations? Because of Bell's theorem and the violation of Bell inequalities. How do we know this? Because it has been proven, and I will come back to this. So we know that we can invent some tables of numbers that do not lead to any violation of non-signaling. They are compatible with causality. They not lead to any paradoxes or causality, any faster than light communication or anything like this, but do not have a quantum explanation. And for that, I will give you a short course on Bell inequalities. Again, I've been making a small detour. I started telling you about devices, about providers, giving you devices, and then at some point I made the transition from I simply changed the provider by the source, and then I made the connection to a Bell theorem, and now I'm more reasoning from a fundamental perspective. Okay, so let's talk about Bell theorem. It's a fundamental result in physics. So we have, again, the source or the provider that prepares two systems. You make two measurements of two outputs. I'm taking two measurements of two outputs because this is the simplest instance of my scenario and gives rise to the simplest and most famous Bell inequality, which is CHSH, Clauser-Orn-Shimoni-Holt, Clauser, a Nobel Prize of Physics in 2022. So these people realize that you can design the following experiment. Again, source, making two measurements of two outputs. I call these measurements now 1 and 2. This is irrelevant. It's only for mathematical convenience, and the outputs are called plus and minus 1. And then you take this expression that you can easily compute in this black box language, okay? So this is the output of the device by Alice when she uses the input 1. And this output A1 can be plus and minus 1. And B1 is the output of this device when you use input 1. Again, it can be plus and minus 1. So here I have a linear combination of products of plus and minus 1. And you can easily see that this product of plus and minus 1 is bounded by 2. Okay, so this is easy. For instance, if you take the assignment in which there are several ways of applying this, you can in principle list all possible assignments of plus and minus 1s here, and you will see that this quantity is never larger than 2. For instance, if you take the assignment that all of them are plus 1, this quantity is plus 1 times plus 1, this is plus 1, plus 1 times plus 1, this is a plus 1, This again a +1, and this is a +1 with a -1. It gives a -1. So you have 3 +1s -1. It gives 2. And you can see that whatever you do here, this quantity is always bounded by 2. Okay, this is a Bell inequality. Very trivial statement, mathematical statement. Okay, the surprising thing is that you can violate this Bell inequality. Okay, so you can prepare a state here in which you make quantum state, which is the maximum entanglement state of 2 qubits. You make 2 measurements of 2 outputs, and you can have that this CHSH expression is 2 square root of 2, which is larger than 2. Okay, this is Bell's theorem. Okay, it's just you can design this constraint on this quantity and under the assumption that these magnitudes have a well-defined value before starting the experiment. So it has to be plus or minus 1. Then you get a constraint on this, and this is classical physics. Okay, in classical physics, the value of these quantities it may vary with time, but it's always defined before making the experiment. And then this quantity is bounded by 2, but this quantity, the value of this quantity can be larger by 2 but in quantum physics. Okay, so I think this is really surprising, I would say. If you didn't see this result before, I hope you are surprised by this, because it's really surprising how quantum physics manages to give rise to this effect. But of course, this is a very simple prediction of quantum physics, and it has been demonstrated in the labs. Okay, so this is what it's telling you, is that the correlations you can get in a quantum experiment are larger than those that you can get in a classical experiment, in particular, because in classical experiment, the value of this quantity is bounded by 2, while in a quantum experiment, it can be larger than 2. This is telling you why you can have this region of quantum correlations with no classical analog. And what a Bell inequality is nothing but a hyperplane in this space, okay? So all classical world is below this quantity, and this is why CHSH is smaller than 2. Quantum physics, you can get 2 square root of 2, and indeed, this is the largest value you can get in quantum physics for CHSH, okay? So you see here, you're simply shifting this hyperplane, and you make it tangent to quantum physics. You only are changing this number here, and all quantum physics is below this value here. And now what you can see is that you take this innocent table of numbers that I was inventing before, given plus and minus and halves. It looks like a very innocent quantity, but actually, if you compute the CHSH value for this quantity, you see here for 1, 1, you could only have plus, plus, and minus, minus. The product of these two numbers is 1, so this number is equal to plus 1. This number is equal to plus 1. This number is equal to plus 1. But this last number, the only possibility is plus, minus, or minus, plus. So the product is always minus 1. With a minus 1, this gives a plus. So you can go up to 4. So this point is impossible in quantum physics. And this is the first example we had of no signaling point that it has no quantum explanation. Okay, so in principle, you could have points in nature. We don't know where to find them because our description of nature is based on quantum physics, in which you could have this table of probabilities compatible with this experiment without running into any causal contradiction, but falsifying quantum physics in the same way as Bell inequalities falsify classical physics. Okay, if you had an experiment, a simple experiment in which you prepare a system of 2 particles, you make 2 measurements of 2 outputs, and you find a value larger than 2 square root of 2, which is in principle possible, you could violate quantum physics, falsify quantum physics. Okay, so what we have here is that I started with this device-dependent approach. Then I was telling you about this characterization of quantum correlations. I was telling you about these sets. Of course, if we want to do quantum device-independent quantum information processing, we are going to use this set, okay? The set of statistical points of correlations that are possible with quantum physics, but do not have a classical analog, because we want to achieve results that are not possible in classical physics, okay? We should better use things that do not have a classical analog. It happens that the characterization of this set is very difficult, okay? I don't have time to tell you why and how we do it, but it's not easy, okay? And we invented a method that I'm going to briefly mention to you. So we invented a method to characterize the set of quantum correlations in the past. Okay, so now let me just put everything together and let's go back to protocols, okay? So now remember my joke. Well, not my joke, the joke I use. I mean, I will give some slides back, okay? So we want to be sure about randomness, okay? Only from the statistics that the device produces. We want to certify that a protocol produces random outputs, quantum random outputs, okay? Here, it's impossible in classical physics. We want to do it in quantum physics. So what do you have to do for that? Okay. Well, if you follow what I was telling you, you have to use Bell's theorem. Okay, so if you want to have a protocol in which you are certain about the generation of quantum randomness, you have to go to the provider, you as a user, and you have to ask for two devices that violate Bell's theorem. Okay, and this is because if you remember what I did for Bell's theorem, the derivation of a Bell inequality was very simple mathematics. So clearly, this bound is true if you buy the initial assumption, which is that the observables have well-defined values, okay? Once you buy this assumption, this is simply mathematics, okay? So you put here plus and minus ones, and this quantity is always bounded by 2. So the only possibility for you to prove, to explain a violation of a Bell inequality is that this assumption is not true. So this is telling you that these quantities have not well-defined values. Hence, they are generating the experiment in an unpredictable way. Because if you could predict them, then it means that you could write them in advance, so you could assign well-defined values in advance, and then you could not violate the Bell inequality. So one of the main lessons of Bell's theorem is that whenever you have some data that violate a Bell inequality, these data had not well-defined values in advance. They were not deterministically written in advance, and then they are simply random. They just appear in the Bell experiment. Okay, so this, if you go to the provider, you ask for devices violating a Bell experiment, and then the Bell violation certifies the randomness of your output. And in fact, this is an intuition, but you can bound the randomness of the outputs from the observed Bell inequality violation. Okay, and this is something we did already some years ago. So you can obtain, using the techniques that we have, the community has, you can bound the amount of predictability. Okay, full predictability means determinism. Half predictability means a perfect coin, a perfect random bit, as a function of the Bell violation. Okay, so remember that for CHSH, the local classical bound is 2. At this point, you have full predictability, as in classical physics. But as soon as you enter the region of quantum Bell violation, the predictability decreases, you have some randomness. And at the point of maximal quantum violation, you have a perfect random bit. Okay, and again, the logic is the same. You buy these devices, you make a Bell test, and from the amount of Bell violation, you can certify a given amount of randomness. At the point of maximal quantum violation, you can certify a perfect random bit, something that is impossible classically. What is important here to understand is that this device-independent scenario always refers to the user, okay? You buy these devices and you want to certify the functioning from the statistics it produces. Of course, if you are the provider and you want to sell your devices, things are never device-independent, okay? If you want that the user buys and keeps your devices, you should violate a Bell inequality, and hence you have to produce the state and the measurements that violate the Bell inequality. But once the provider does this, the provider packs everything into these black boxes. These are given to the user, and the user has to say things about the devices in a device-independent way. And the same idea now can be used for cryptography. Actually, I'm telling you historically in a non-chronographically order, okay? So we first came up with the idea of QKD, of quantum distribution, but the idea is the same. Now, instead of running the Bell test, the user running the Bell test on their lab, you have Alice and Bob, they run a Bell test at distance. And if they see a Bell violation at distance, they know that the outputs are random because of what I told you before, but it's a measurement on a maximal entanglement test. So they know that the outputs are correlated, and correlated randomness, shared randomness is the secret key. Okay. I'm now going a bit fast here, but I hope you understand that if I have something random and a friend of mine has something also random but correlated with me, this is a perfect secret key because it's random and it's not predictable by anyone else, private, but this is shared only by Alice and Bob. Okay, so again, I'm presenting this for crypto, for randomness, but this is a general language, okay? So you use this to make protocols, and to make protocols with self-certified performance only based on statistics. So I don't have, to, of course, time to tell you about these possible applications, and I'm going to focus very quickly on something in which we use this idea to obtain any result in quantum foundations. Okay, so device independent, in a way you can understand it as you use one of the main fundamental results on quantum foundations, Bell theorem, and you did protocols for randomness and cryptography based on Bell theorem. So now I'm going to reverse this arrow, and I'm going to use some language or techniques from quantum information theory to solve an open problem in quantum foundations. Okay, and this, I will go very quickly here. So this is just about a result we published now 2 years ago on the falsification, on the use of the need of real numbers in quantum theory. So also one of the surprises in quantum theory is that it's the first theory in which things were phrased in terms of complex numbers. Okay, so if you take the standard formulation of quantum theory based on Hilbert spaces, okay, you open the postulates and you immediately find first postulate to any physical system you associate a complex Hilbert space, okay, and then you have postulates about states that are vectors, measurements, how you compute probabilities, and how you compose systems. Okay, these are the postulates of quantum theory. And of course, you may wonder, okay, why complex? Okay, it's the first theory in which the postulates are phrased in terms of complex entities. Okay, I mean, you take electromagnetism, the electric and magnetic field are real fields. Okay, I mean, sometimes we use complex numbers to simplify calculation, but there is nothing in the postulates phrased in terms of complex numbers, and the same applies to classical mechanics. And this worried the fathers of the theory. Okay, so this is something that the letter from Schrödinger to Lorentz, where he even conjectured that probably psi, even if it was complex vector, fundamentally it was a real function. And so these people have wondered about this question, and they wonder whether, okay, what happens if I take the same postulates of quantum theory and I simply replace my complex Hilbert space by a real Hilbert space? And this question has been studied. So is it a different theory? And what does it mean? Of course, it's a different theory, but the question is whether it gives different predictions, experimental predictions, okay? Because if at the very end, the two theories give the same experimental predictions, then the use of complex numbers is just a matter of convenience, maybe because it simplifies some calculation, as it happens, for instance, in electromagnetism. Okay, this is why people have, in foundation, this is a question that has been considered from different perspectives, okay? And what you can see is that the question is not easy, okay? And what you have to understand here is that, of course, I'm comparing complex quantum theory with real quantum theory. And in doing this thing, I want to do it with arbitrary Hilbert spaces. Okay, so for instance, imagine you have an experiment in which you make a measurement on a quantum state. Okay, this is the Born rule. Everything is complex, okay? In real quantum theory, you can always describe this experiment, okay? So you can see, the only thing you do, okay, a complex number is still real numbers, so you suspect that you will have to double the Hilbert space dimension of the size of these matrices, because you have to accommodate the same number of parameters, and a complex number is two real numbers. So I double the dimension, so you attach a qubit to the previous system. Okay, and what you can see is that if you take the state and the complex operators you use, and you make this trick, you turn them into real. I don't have time to tell you. You can reproduce the statistics of this experiment with real quantum theory. Okay, so this is known since decades. So people then try to go, okay, maybe we have to go into a Bell theorem and prove that the real quantum, make a Bell theorem for real quantum theory, but it can be proven that this is no longer possible. Okay, this was proven in this paper. So what we proved in this Nature paper 2 years ago was that if you go to a more complex device-independent scenario with more boxes and more states, then you can prove that real quantum theory and complex quantum theory are different theories. They lead to experimental predictions. Then you can make the experiment and you can falsify real quantum theory and really prove that quantum theory needs complex number to explain all statistics you can see in nature. Okay, this has been quite fast, but just to tell you that the same techniques we use that we adopt from quantum foundations to make protocols, we can take them back and prove things again back in quantum foundations. And then the experiment was performed and then real quantum theory was falsified. Okay, I don't have time to go into that, so I will go to the conclusions. You see, I have many things. I knew I was not going to explain all these things. So let me just go to the conclusions. So I was telling you about, no, sorry, this is not what I want to do. Yes. Okay, so I was presenting you the device-independent scenario. So our main motivation to go into these protocols is because they give you self-certified performance. Okay, so you don't have to make any assumption about the modeling of your devices. If they give the right statistics, they violate a Bell inequality, sometimes by a given amount, then you know that they perform as expected and you can use them for a protocol. And in this black box quantum information theory, you have to deal with statistics that has no classical explanation. And this is the only statistic that does not have classical explanation is the one that violates a Bell inequality. Okay, this is why Bell's theorem was invented, just to prove, to design a statistical experiment that has no classical explanation. Okay, now we are using this as a resource to make quantum information protocols. So we have protocols for randomness generation, secret key distribution. There is something called self-testing that I didn't explain. So what we want to understand is what you can do in this black box scenario. Of course, it's nice because you make minimal modeling about your devices, but of course it has some limitations because you don't assume much about your devices, and then protocols are sometimes more difficult. I didn't have time to discuss about implementation. I can get questions on that. They look simple, but they are hard to implement. Okay, and this is because you need something called detection loophole-free violation, and this is challenging. It is challenging when you are a single user who wants to see a Bell inequality violation to generate randomness, but it's even harder if you have a Bell inequality violation. You have to see a Bell inequality violation at distance between Alice and Bob. Okay, so this is challenging. And this framework, I mean, I don't have time to tell you all these applications, but it can also be used for quantum foundations. I quickly told you about this complex real quantum theory. And we are also using this in the context of many body physics. So we use the same language to certify properties of ground state problems that can be used in the context of quantum simulation. And I think more in general, okay, this is a very timely and transversal question, okay, the question of quantum certification. You are given these devices, you are having these complex many-body systems in the labs. Full reconstruction is impossible, tomography is impossible. You will only have access to a fraction of the possible measurements that you can implement. And out of this partial information, you want to certify interesting properties like whether systems are entangled, secret, perform a quantum computation, random, and so on. Okay, that was all. Thank you very much for your attention.
Thank you very much, Tony, for this wonderful talk. Now, anyone interested in asking a question can unmute himself or herself and ask directly to Tony. Okay, so maybe I can start. I was really interested in this part of quantum mechanics formulating in terms of real numbers. Quite interesting. And I wanted to ask if beyond this aspect of not being able to reproduce this Bell nonlocality in this real theory, is there anything known about these bounds in the CH-SH bounds for this theory, or is it just, or the result is just simply that you don't recover standard quantum mechanics correlations?
Yeah, so if you look at sorry, I have many slides, I should have cut them. So you look at what I explained you about CHSH, no?
Yeah.
You are familiar about the evaluation of CHSH, okay?
Yeah.
So the way we evaluate CHSH, for instance, through this state, okay? This state, if you write in the computational basis, is real, okay? And the measurements I'm presenting here, you can take these measurements that are in the XZ equator of the block sphere. If you look at the XZ, is a linear combination of sigma X and sigma Z. These are linear, these are real operators.
Okay.
So 2 square root of 2, you can get with real quantum theory. So
okay.
CHSH is not a valid test for real quantum theory, okay?
Okay.
So I went a bit fast in what I was telling you. In fact, so people tried to falsify real quantum theory, and they first realized, I was a bit fast here, okay? First, they thought about the simplex experiment in which, okay, you prepare a state of a particle and you make measurements, and they realized that they cannot falsify real quantum theory because there is always an explanation. And then people thought, okay, what is perhaps the most useful setup we have in foundation? And they thought, oh, it's the setup in which I prepare an entangled state and make local measurements, like in a Bell theorem, okay? And then I didn't have time and I went very fast, but you can prove that in this scenario, you can, whatever you can do in complex quantum theory, you can do in real quantum theory in the standard Bell experiment, okay? In particular, you can get to CHSH 2 square root of 2, okay? And this is because in this Bell experiment, you prepare an entangled state and you send into different locations and you make local measurements. The main novelty came because in this device-independent scenario, we are lately studying a variant of the Bell scenario in which you see here, I have these boxes, but I prepare different states. And I also assume that these states that I prepare are independent. Okay, so I put tensor product on the measurement, but I also put tensor product on the state. You see here, because if you describe this setup in quantum physics, okay, according to our quantum intuition, no, you have a state, tensor product, another state, and measurements with tensor product. And it was because we made this slightly more elaborate network that we could falsify real quantum theory. In fact, people thought that, I believe people thought that there was no way of falsifying real quantum theory. Okay, it was only when we had this idea of making a more complex network with independent preparations and independent measurements that we could falsify real quantum theory. So if you look at any standard Bell inequality violation, the value you can get with complex quantum theory and real quantum theory is the same.
I see. Thank you very much. Is there any question from the audience? Doesn't seem very much. And okay, it's fine because since we are already a bit late, because this usually don't take this long, maybe we can wrap up here. If there is any last second question. This means that the talk was pretty clear.
Well, this is a possible interpretation, yes.
Well, for sure, it was very introductory, which for sure is the kind of thing that we are looking for in these conferences. So, thank you very much, Tony, for this wonderful talk.
No problem. See you around and have a nice break.
You too.
Bye
Bye.
bye.